Welcome back to our Huawei eLearning course, SDN Architecture and Ecosystem. In the second chapter, we will talk about SDN architecture. I will give you an overview about the SDN architecture. We will talk about the SDN architecture in general, and then we will talk about the infrastructure layer, the control layer, and the application layer. As already said before, the basic SDN model consists of three different layers. The application layer, which covers solutions that focus on the expansion of network services. These solutions are mainly software applications that communicate with the controller. The control layer, which includes a centralized SDN controller that maintains a global view of the network. It also gets requests through clearly defined APIs from the application layer and performs management and monitoring of network devices via standard protocols. And the infrastructure or data layer, which involves the physical network equipment, including switches and routers. This layer provides programmable and high-speed hardware and software, which needs to be compliant with industry standards. Network devices of the infrastructure layer are configured by the control layer via, for instance, OpenFlow protocol. Let's talk about these three individual SDN layers in some more detail, and let's start with the infrastructure layer. The infrastructure layer or data layer is the bottom layer. It mainly consists of forwarding devices which are responsible to forward traffic. Therefore, these devices need to store forwarding tables for layer 2 and for layer 3. The entries for the forwarding tables are calculated by the SDN controller, not by the forwarding device itself. So each networking device of the infrastructure layer belongs to one SDN controller. Infrastructure layer devices basically report the network resource status information to the control layer and receive forwarding information from the control layer. The interface between the infrastructure layer and the control layer is called southbound interface. There are various protocols defined for this southbound interface, such as OpenFlow, SNMP, PCEP, or OVSDB, just to name some of them. Now let's talk about the control layer. The control plane layer represents the core of the SDN architecture. It collects the physical network state information, is calculated routing algorithm, and delivers entries for the forwarding tables to the network devices. The control layer function is realized by the SDN controller. Control layer provides a northbound interface to the application layer and a southbound interface to the infrastructure layer. Sometimes this component is also called the Network Operating System, NOS. Now let's come to the third layer of the SDN architecture, the application layer. The application layer covers an array of applications such as OSS or OpenStack. The operating support system OSS handles network services provisioning. OpenStack is used in data center networks. But the application layer can also provide other applications such as security applications, service provision applications, etc. And as for protocols running on the northbound interface, the control layer provides, for example, RESTful protocol, netconf protocol, or other open API protocols. Now we will look at the challenges an SDN controller has to face. First challenge is reliability. The difference between the distributed network architecture in traditional networks and the centralized network architecture with SDN controller as the core of the network are as following. The traditional network has a fully distributed network structure where each networking device is calculating the forwarding table entries independently. Each router in the network collects link state information as material for the routing algorithm to calculate the shortest path to a destination. Any change of network topology will trigger the routers to flood the new link state information and recalculate the new route independently. So traditional networks have an automatic network convergence upon failure. This mechanism provides the highest reliability. In SDN networks, the network convergence depends on the SDN controller, as the controller provides a centralized control in the SDN network. As a result, this introduces a single point of failure. If we talk about reliability in SDN networks, there are 4 weak points highlighted in this picture. First, the server where the controller runs may be faulty, for example, server shutdown due to power outage. Or second, the controller software may fail. Or third, the communication between the controller and the forwarding device, the southbound interface, can be interrupted. Or some disaster may happen in the data center where the SDN controller is located. This might also affect the respective controller. Let's think about solutions to solve these mentioned reliability issues. Issue 1 was that the server where the SDN controller is located may fail. Well, to avoid this scenario, we suggest to deploy a solution with server redundancy. Dual device hot backup shall be implemented based as following. 2 controllers are specified on a forwarder. When priorities are configured for the 2 controllers or an election mechanism is used, then the forwarder selects a controller as the active controller for service forwarding. The other controller will be acting as standby controller. Service control data on the active and standby controller must be the same for the dual device hot backup scenario. After an active standby controller switchover is performed, the new active controller takes over without need of reconfiguring service control data. As shown in this figure, the forwarder are dual-homed to 2 controllers, A and B, which functions as the active and standby controllers respectively. If the active controller, in our example the controller A, fails, then the backup controller, in our example the controller B, takes over as active controller for the forwarding devices. How to solve the problem with reliability issue 2, that the controller software may fail? Well, we may solve this issue with a distributed SDN controller architecture. In a distributed controller architecture, we have several servers or virtual machines where the controller hardware is located. For each of those, we provide a commercial OS. Then there is one extra layer called the system middleware. This layer provides a monitoring process to monitor software status between the nodes of the monitoring cluster. And there is the network OS, which also provides a distributed backup concept for each of the running processes. And on top of that, there is the service application layer, which provides a backup for each running ape application process. So you can see that this concept can provide redundancy for each of the SDN controller layers and processes. How to solve the issue 3, that the communication via the southbound interface between the controller and the forwarding device may be interrupted. First, the solution shall provide interface redundancy, which allows to send and receive packets on each Ethernet interface of the controller. Second, the controller shall be connected to the forwarding network through at least 2 links to provide redundancy. And third, the controller shall be connected with the forwarding network through a dedicated management network. And finally, how to solve the issue 4, that some disaster, for instance, a natural disaster, is happening at the data center where the SDN controller function is located. To solve this issue, we need to provide a disaster recovery center at a remote site. So active controller and remote backup controller shall provide dual node hot standby. Another challenge for the SDN controller is performance. This slide shows 2 basic performance requirements for the SDN controller: time and space. Time, the failure convergence time of a network with an SDN controller deployed must be close to that of a traditional network. So convergence time should not be worse than in a traditional network. And space, the data center must have the ability to support millions of Open vSwitches. On the data center interconnection network, each controller needs to manage 2,000 devices. And for the IP RAN access scenario, each controller needs to control 20,000 devices. Let's have a look at the time requirement of an SDN controller. There are some differences according to the convergence time between a traditional network and the SDN network. In a traditional network, the total convergence time T1 in case of failure would be the sum of the fault detection, the notification time for the entire network, and the time for local route recalculation and the time for local routing updates on each router. In an SDN network, all forwarders register and communicate through the southbound interface via, for instance, Open Flow Protocol with the controller. So the controller has the global view of the topology. Once the fault occurs, the total convergence time T2 would be the sum of the fault detection time, the time for a forwarder to notify the fault to the controller, and the time for the controller to calculate a new route, and the time to update all the routes of the forwarder. To shorten the SDN network convergence time, the centralized route calculation time T3 and the route update time on the controller T4 must be shortened. The fault notification time T2 is shorter than the T2 in traditional networks. So the key to shorten the SDN network convergence time is the algorithm, the hardware performance, and the distributed computing capability of the controller. Let's have a look at the space requirement of an SDN controller. The SDN controller must be able to control large-sized networks. The major building blocks to provide that are shown on this slide: concurrent data sending and receiving of multiple servers, dynamic deployment of scale-out to adapt network resources, distributed memory database, and distributed parallel calculation of paths. All these are requirements which will lead to that SDN controllers are able to control large-sized networks. Another challenge for the SDN controller can be seen in its openness capability. A characteristic of SDN is that its interfaces should be standard-based and vendor-neutral. If SDN controllers can provide that openness, this will clearly simplify network design and operation, because instructions are provided by SDN controllers instead of multiple vendor-specific devices and protocols. And if supporting openness, the network control can be directly programmed at the controller because it's decoupled from the forwarding functions. Within an SDN environment, the apps running on top of the SDN controller are providing the higher level orchestration and programmability of the network. Also for this northbound interface, the openness is an important requirement. There are two different approaches for that: the client-server model and the embedded programming structure. It is recommended to use the client-server model to provide open source and programmable APIs, for instance, RESTful API. Here we have a loose coupling of applications and controllers. This provides the opportunity for independent deployment with no restriction or limitation on programming language, platform, or deployment location. Here the app and the controller are independent of each other. Most of the controllers support this mode. The other model is the embedded programming structure model. Here we have some restrictions by the programming language, for instance Java. Then this model depends on the platform, on the deployment location, because it runs together with the controller. For example, applications that run on Microsoft Windows or Apple's Mac OS are based on this structure. But the advantage of this model is that its performance is better than the performance of the client-server model. But SDN does not only need to provide open northbound interface support for applications, it also needs to provide open southbound interface for the support of multi-vendor forwarders. In order to solve the multi-vendor hardware compatibility issue, vendors can adopt a standard OpenFlow protocol so that controller is able to communicate with the forwarder and advertise flow table directly to the forwarding device. Or controllers may also support vendor-specific plugin functions. So this model gave an overview about SDN architecture, with some focus on the individual layers of SDN architecture and also about the challenges an SDN controller has to face. Thank you for watching.